Okay.
So here is a special, just the empty set, here is empty set, here is empty set problem. But this is not because it has a one element. Because the empty set that there are no element. So this set have one element. Although this element is empty set, but altogether they are just not empty set because they have one and one. So we just using the logic expression to define the set operation. Now we just use the logic expression. So just from this logic expression, and we can make the computer to understand why A and B they are not equal or equal. Just based on this logic expression. Or the logic expression can be easy to do their computation or do their reference or do some just the influence by their rules in the logic rules. Okay, so based on this logic expression, and computer can do a little bit the complex things such as that do the state operation. Here just to check whether or not the two sets are equal. Just based on this. And for this, we have already for our human, in human language, we just say that you have just define the set, we tend to care about the duplicate element. So what means a duplicate element just like this? If x belongs to A, if and only if x belongs to B by condition. So one is belong to A, and also one is belong to B. So they are equal. So although they have from this definition, computer can understand well about the duplicate element then to affected the state vector.
and this would be set A, and this would be set B. So essentially what I'm saying is anything in set A is also contained in set B. So let's say A is the set of elements 1, 2, 3, and B is the set of elements 1, 2, 3, 4, 5. So if I were putting these values on my pen, 1, 2, and 3 would all be in set A. 4 and 5 would be in set B, but notice that everything in set A is also contained in set B. So this would be a subset. Again, this is the notation that we would use. We're saying for all x's, if x is an element of A, then x is an element of B.
So just from this symbol, you also can find some a little bit the relationship between the set operator and the logical operator. You will find for this symbol, it is just have the open, and here just here the arrow that have the have just the arrow direction, and here is also this the open direction, and we have no the previous relation just equal, and here is by condition equal. That equal symbol just the logical by condition, and the subset just this it is the condition.
And then this is the notation that we would use. So I want you to kind of think about this as like a less than or equal to B, essentially saying everything in A is in B, and maybe they're exactly the same, but maybe they're not. So a little bit more on subsets. If I'm going to show that A is a subset of B, essentially I have to show that every element of A belongs to B. Oops, belongs to B.
It's just from the definition of the logic.
To B. So I'm saying if X belongs to A, then X belongs to B. Now, why is it important to know this? Because obviously there will be some proof involved, and this is the way that we will go about that proof, is to show that if it belongs to A, then it belongs to B as well. Obviously, if I want to show that A is not a subset of B, all I have to do is find some example that shows that it's not true, essentially. So I'm going to find an element. If there exists some element X that belongs to A that does not belong to B, essentially is what I want to do. So show it belongs to A, belongs to set A, but not set B. And the last one says, show A is a subset of B and B is a subset of A. Now, why would this be important? Because if this is true, thinking about it this way, A is less than or equal to B, B is less than or equal to A. If both of those are true, what could we state? We could state that A is equal to B. So that's essentially what we're going to do. And this one's super important because this is how you will prove that A is equal to B, is to show that both of those statements are true. So you're proving that the subset of A, or that A is a subset of B, that B is a subset of A, and therefore A and B are equal sets. So now that we understand a subset, it's important to understand the difference between a subset and a proper subset. So with our subsets, we said A was a subset of B, and we used this line to denote that they could in fact be the exact same set. So here we're talking about a proper subset, and note how my notation is just going to change a little bit. A proper subset says that A is a subset of B, but that they are not equal to one another. Therefore, we have some element in B that's not contained in A. So let's say A was that set of 1, 2, 3. If B was the set of 1, 2, 3, I could say A is a subset of B, and B is a subset of A, and therefore A and B are equal sets. However, if B is now 1, 2, 3, 4, A is still a subset of B, but B is not a subset of A. These are not equal, and therefore A is a proper subset of B, and it's proper because we've got this one little guy in set B that is not contained in A. And again, here's the longer version using our predicate logic. For all x's, if x belongs to A, then x belongs to B, and there exists some element that belongs to B and that does not belong to A. So that is a proper subset. So now we want to talk about cardinality. And cardinality is just essentially the size of your set. So cardinality is the number of distinct elements of a set, and of course, distinct being important here. Let's say set A is 1, 2, 3, 3, 3, 4. Then the cardinality of A, and notice that notation is just using essentially like the absolute value bracket on each side. This is saying how many distinct elements are there? There's 1, 2, 3, 4 distinct elements. So 3, 3, 3, there's 3 of them, so those aren't all distinct, but you get the idea. So the notation, again, is just, that's what tells me that I'm finding the cardinality or the number of elements in the set. So let's say I wanted to find the number of elements in the set of the alphabet. Oops, maybe try to spell alphabet correctly. Well, there are 26 letters of the alphabet, and so that would be the cardinality of that set. The cardinality of the empty set, hopefully we all know that's 0 because the empty set is saying that there is nothing in the set. Now I want to introduce you to a couple of concepts that really, this is just an introduction, but as we move forward through this course, we will use these concepts again and again. So the first of those is the power set. And the power set is the set of all subsets of a set. So for instance, let's say set A is 0, 1, 2. If I want the power set of A, then I want all of the subsets. So the subset would be the empty set, because again, I'm looking at these elements. I could have none of those elements. I could have one of those elements. So 0, 1, 2. I could have two of those elements, 0, 1, 0, 2, or 1, 2. Or I could have three of those elements, 0, 1, 2. Now keep in mind, because order doesn't matter, I wouldn't have to write 0, 1, and 1, 0 because those are the same set. So how many elements does the power set have? 1, 2, 3, 4, 5, 6, 7, 8. So the cardinality of the power set of A is in depth about this later, but if you ever want the cardinality of the power set of a set, whoa, getting crazy, of a set with n elements is 2 to the n. So here I had 3 elements, and therefore 2 to the third was 8, and that is exactly how many we found. So this brings us to tuples. And a tuple is important because basically it's an ordered collection that has A sub 1 as its first element, A sub 2 as its second element, etc., etc. Obviously, the way that we would have seen this most often is in ordered pairs. So A comma, say A1 comma A2, you get the idea. It's basically just two values, but the important thing here is that it's ordered. Whereas when we're just looking at a normal set, we don't worry about the order, but ordered pairs, obviously, the ordered pair of 5, 2 is not the same as the ordered pair of 2, 5. Those are very different points on our Cartesian plane. So I bring up ordered tuples because of the Cartesian product, which we will talk much more about when we talk about relations further along in this course. But it's essentially the set of ordered pairs, A comma B, where A, each element A belongs to the set A, and each element B belongs to the set B, resulting from A times B. So let's say set A is 0 and 1, and set B is 2, 3, 4. What a Cartesian product tells us to do is it's going to be all of the ordered pairs that I can create using one element of A and one element of B. So I could have 0, comma 2. I could have 0, comma 3, 0, comma 4, or I could have 1, comma 2, 1, comma 3, 1, comma 4. So again, each time I used a value from set A and an element from set B, and I've done all of the different combinations. Again, I said later on we'll talk about relations, but let's say I had a subset R that included just 0, 2, and 1, 2. This would be considered a relation because it is a subset of that Cartesian product. Lastly, let's take a look at what is called a truth set. A truth set of P.
And just for this notation, why we just using the Cartesian product or the set product. And this set product means we are just going to make their relation between the two set A and B. And in the future, the function and relationship and matrix just based on this. So this the Cartesian product of the two sets is very important. That means in the computer side, the function and metrics in the letter we are just detailed this, but in computer world they are all same as the tuple or coupled set. That means they are also the special set. This is the special set. But for each of the set, they are just the combined two elements, one from the A and the second is from B, but they have order.
This would be considered a relation because it is a subset of that Cartesian product. Lastly, let's take a look at what is called a truth set. A truth set of P is the set of elements X in the domain such that P of X is true. So obviously this is some sort of propositional function, and we're saying the truth set is any values that make P of X true. So our notation says X is an element of D. D is obviously the domain, such that P of X is true. So let's say the domain here is the integers, and let's say P of X represents the statement that the absolute value of X is equal to 3. Well, if that's the case, then the truth set would be the set of all values that I could put in here to make it true. So what values of X would make the absolute value of X equals 3 true? And of course, that would be negative 3 and positive 3. So that would be the truth set because I'm looking for any values that I can plug in for X and get a true value. So the absolute value of negative 3 is 3, and the absolute value of positive 3 is 3. Coming up next, we're going to take a look at operations on sets. you'd like to look at. And the definition of the union of sets is essentially the union, which think of sets is I think about it as a cup where you would put everything from set A in there and everything from set B, all of the values A and B sets together. And since we don't have to worry about duplicates, then we don't worry about it. So here in the Venn diagram that I have drawn, we can see that set A is the set that includes the elements 1, 4, and 7. And set B, because that was everything contained in the set A circle, 1, 4, 7. And in set B, it contains the elements 4, 5, and 6. And so A, 4, and notice 4 is listed twice, but I'm only going to list it once, 5, 6, and 7. So using my picture, it's essentially everything here in either circle, including this part in the middle that's contained in both. So 1, 4, 5, 6, 7 would be all of the elements in the union. So we're looking for anything that is in one or the other.
Okay, here just we using the another this set operator, the unit, and we also using the logic expression to define this set operation unit. We just using the or. So you will find the symbol is very similar. You will just this logic operator symbol, logic symbol is the set object symbol. So it is also open the app. So you will find some it is some the similar things between the set and this the logic. Okay, so we just using the logic to define the set, and in fact, because it is you will find that the definition is if and only if. That means if we just have this the set, we also can define this the logic expression. And from the logic equation, we can define the state. Okay, for computer, that means we're just using this logic expression to understand what it means the set operator. And for our human, we are just using the set operator to model this logic expression. So it is just a different view using the different expression.
So again, you can think of this as an or. Down here, I've included our inclusion, exclusion formula. We talk a lot about that later on, but this is essentially the formula that you would use. Here, if I had A union B, I could take all of the elements of A, which would be 1, 4, 7, and add all of the elements of B, which is 4, 5, 6, and then I'm just going to subtract anything that's here. And we haven't talked about this quite yet, but this is the intersection. And the intersection is here where it's in both sets. So I would subtract 4. And as you can see, what happens there is that just one of those 4s go away. And I would be left with 1, 4, 7, 5, 6, which is the answer that I came up with before.
Okay, now we have 5 minutes break. Okay, we continue to talk about the set. And in these previous sessions, we have already known about the logic expression for computer. But now, in this session, we just to introduce the set and this set for computer to understand what is the means the set. And we're just using the existing the logic expression to describe what you mean the set and the set relationship and the set operator. Okay. And here we also have to show you from the video the general the set meaning, and sometimes is just Cartesian the set. The Cartesian set is very important for just it is just want to make the relationship, because we know that if we have the some the relation just means they have the pair the A and the B. So we are just using the pair set to describe the relation. And in the picture, the function also can be seen as a special set. Okay, so this Cartesian the product the two set is very important for in the future. And here just give you some the example. And we also have this relation. It means the relation concept. The relation is the subset R. This means subset R is A. We just sometimes can means A times B. It's just to for the short Cartesian product A and B. It is if R this is the subset. So here is the set. If this set is a subset of this A times B, then we call it the relationship. So you will find every is a subset of the Cartesian product is a relation. So you will find it is maybe the different the meaning for the relation between our human and the computer side. in human means relation, for example, you are just a human relation, maybe they have something, there are common things or there are common features of their relation because the father and son and the parent and the grandmother, this is a relation maybe. But in the computer, they just say, if you just to describe this relation, they just that they have a special subset of your just the whole pair set. So if each is a pair set, then we can say it is a relation. So in the computer side, the relation is a special set. The special set, it is a subset. The relation is a special set, subset, okay? And here, it is just show you about maybe it is just the order, the different order, maybe they have different subsets. It means A times B and B times A. You know, although it's A and B is the same set, but their final result is not the same. So it is different because they are just the pair. So their pair have but then the pair. So the BA, B2 is not equal to B. They are different meaning for the relationship. For example, they're just the father and son. They're just the son and father. Maybe they have different. Okay. That means the A is father, B is son. You cannot say A is son, B is father. They are different. Okay. And here is the general Cartesian that just have the more relationship. Okay? And, just use the set notation to modify the symbol together with modifying the symbol also this. This is just the tools I've already shown in the video. And the set operator. And for the set operator, that means we are just also using logic expression to describe the set operator definition. It means here we're just using the logical or to describe the set unit. So in fact, we have already to describe set equal. We're just using by condition, and we already said the set, the subset, just using the by condition. And here the union, we are just using logical or in fact, next we are just said intersection, we are just using and. So you will find it is a special things. This logical basic the symbol. And we know that if you just use the not, we have already the not. And here just means that it may be the not, uh, not symbol or not include. So the state operator is sometimes can be the map one-to-one to the logical operator intersection. So for the intersection, we're just using this intersection, we're just using the logical and describe the intersection. And this the video to more tell about this meaning.
So the intersection says if or if the union was sort of like an or, this is sort of like an and. And I'm saying the only way that it belongs at the intersection is if it's in set A and B. So here I'm saying A intersect B is the sum of all x's such that x is in A and x is in B. So looking at my picture, before we get to that part I've written in blue, looking at my picture, I can see that the intersection A intersect B in this example is just 4. Because here I'm looking at a 4 that is contained in A, because remember A was 147 and B was 456. And so the intersection is only elements that they have in common, and in this case, that is only the element 4. So what I'm saying over here in blue is I'm saying if the intersection is empty or the empty set, then A and B are said to be disjoint. So that's just another little vocabulary nugget that you can file away. Disjoint, my Venn diagram would look more like this because there would be no intersection or no elements that were contained in both sets A and B. Complement is another operation or another concept that is really important to understand. And the complement of a set is essentially any elements that are in the domain or in the universe that are not in that set. So here, as you can see, I've got not A, so it's kind of like not P of X, where P of X is any element in set A. We're essentially saying it's anything that's not in set A that's in the universe. So you might also see it written like this. That is the complement of A, but this is the way that I'm going to be writing it, not A. And essentially it says it's in not A if X is in the universe, but X is not in set A. So let's take a look at our picture where I have set A and set B. So set A is everything inside of this circle, which is 1, 4, and 7. So the set not A would be any number that's not 1, 4, and 7. So I would say set A is 0, 2, 3. Notice these are all out in the universe. Still 5 and 6, even though those are not just out here hanging out, they're in set B, not including the 4, but 5 and 6 are not in set A. And then, of course, 8 and 9. So not A would be 0, 2, 3, 5, 6, 8, 9. Let's say I wanted not B. Again, that's all the digits from 0 to 9, but I couldn't include 4, 5, 6. So it would be 0, 1, 2, 3. 4, 5, 6 are all inside B, so 7, 8, 9. Those are all of the not B. And of course, you can get crazy and you can say, well, A union B or not A union B. So remember, A union B, erase my little markings here. A union B is everything inside A or B. So not A union B would be anything that's not inside A or B, which would be 0, 2, 3, 8, 9. So all of those values on the outside.
So here is just to state the operator complement. So this complement is referred to just the logical operator not. It's not means just is not. So you can sometimes can call it a not, and it's a complement relationship between the logical operator and the state operator.
Could do A intersect B and not. And again, A intersect B is just this part in the middle. So not A intersect B would be everything else, which would be 0, 1, 2, 3, not 4, because that's the one in the middle, 5, 6, 7, 8, 9. So hopefully we understand the concept of a complement. And we're going to now look at the difference. The difference is essentially the set containing all of the elements of set A that are not in set B. So here I'm looking at A minus B being the set of all x's such that x is in A, but x is not in B. So in this case, looking at A minus B in my picture, my only options are 1, 4, and 7. But I need to take away any of those that are also in B. So my solution will just be 1 and 7. So that is or those are the values that I would use for the difference. So essentially I'm just subtracting anything that is contained in B. I couldn't include include numbers like 0, 2, 3, etc., because those were not contained in A to begin with. So it's just like a normal subtraction question. Here is a question that I would really like for you to try. This is just a great practice question, like you might see in homework, just to make sure you understand the concepts of subtraction or complements or unions, etc. So go ahead and press play and try this question. And I'm sorry, press pause, try this question, and then press play to see if your answers match up with mine. So before I get started, I really am going to rewrite set B in roster notation. So I'm just going to list out all of the elements of that set. And again, I don't care for writing them more than once. So even though I've got two E's, I'm only writing E once. M, A, I've already used T, and H. And again, if I wanted to, I could certainly write those in alphabetical order, but really it's not going to matter. So my first question asked me to find the union, and union is kind of like the cup, and the cup contains all of the elements in either set. So set A is A, E, I, O, U, and then I'm going to also include everything in set B, but I don't have to rewrite A, E, I, O, or U. So I've got D, S, C, R, don't have to write E, T, M, H. So all of those elements would belong to the union. The intersection would be only those elements that are in both A and in B. So I can see here I've got an A in both sets. I've got an E in both sets. I've got an I in both sets. I don't have an O and I don't have a U. So the intersection would just be A, E, I, and the O and U are not contained in the word discrete math. A minus B, actually I should have left those. My bad. Unfortunately, it's not going to let me just undo. So H. All right, so now I'm looking at A minus B, which is essentially starting with A, E, I, O, U. I'm saying if I take away any values that are in B, what would I be left with? Well, it's kind of nice because I've already found the intersection, and I know that B includes the values of A, E, I, and so if I was taking A, which is A, E, I, O, U, and taking away anything in set B, I would be left with O, U. The other way around, starting with B, but getting rid of anything that they have in common, which again, the only things they have in common are A, E, I, would be the set of everything left over, which would be D. Let me just go ahead and underline that. E, I, and A. So anything I didn't underline would be D, S, C, R, T, and H. My next question says the complement of the intersection of A and B. And so remember, the U is the universe of all of the letters of the alphabet. And I'm saying anything that's not in here that is in the alphabet. So my solution there would be B, C, D. So I skipped A, I skipped E, F, G, H. I'm going to skip I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, with commas in between all. And essentially that's all of the letters of the alphabet that are not contained in the intersection. So here was the intersection, AEI, and all of the rest of the letters. And last question, is a subset of B? That is to say, do all of these values belong in B? And it doesn't matter if B has extras, but this is obviously, or hopefully obviously, a no. because we already determined previously that O and U are not contained in discrete math.
So this is the practice question just for our human. That means if you just do in my human brain, we are just using our human understanding or human natural language to do this question. Okay, but if how to computer to do it, maybe they are different because they are just translate these all of these set operator into the logic operator. But we know that the computer just have the code machine and the code machine and the low level is the low level just the only and just the circle, the discrete circle. So it just to translate all of them into the logic expression, and based on logic is the equation to their give them the inference, logic inference. That means, for example, if just to check A just union B, it translates to just using the logic expression. That means for all A, if x belong for x for all x, if x belong to A, then x belong to B. Using this, that means we can say it is just using this. And if just for the union, that means they are just using the logic or x belong to A or x belong to B. So that is, and is just also using the logic we have issue is logic complement or this difference. Okay, just using difference like this. A difference B, or we sometimes just for short A minus B, we're just using this logic here. This logic x belong to A and x not belong to B. So, in the computer world, just do like this. The set operator, but in our human, we can just use this picture, but in computer, you cannot do this picture because in the computer can only have this logic choose just do them the choose the keyboard or choose their operator or influence. Okay.
In this video, we're going to explore some set identities that you'll want to know moving forward. So we have several set identities that we need to know, and these words should look familiar to you because we did talk about these in predicate logic.
And this set identity, that means we have already shown about, that means we have said the set operator is sometimes a relationship between the logical operator and set operator. They have just now we also want to give some the same things. That means equivalence because we know that we have the logic equivalence, and now this logic equivalence has sometimes referred to the the state equivalent. We call it the set identity. Set identity. And from this set identity rule, you will find it maybe the similar for the logical rules. This is the set rules and it is very similar as logical rules. Okay. For example, it is just if we just here the P and here is O. P O P with just the logical P. Here P and P is logical equal to P again, simply. And here we can say not P, it is equal to P. So it is very similar. Okay.
We have identities, kind of like the A can be or type of identity. We're saying if I take set A, I take the union of that with the empty set, my result is set A. And that should make sense because we're essentially saying, something plus 0 is whatever you started with, which is the kind of identity. If I take A and reject U, so that's different. We're saying A combined with everything from U, but as the intersection. So as I end up with A because it's only.
Here U means just the whole set, universal set. And if you just refer to the logic expression, it is just mean that logic expression to show you about this. And because we have already to have the just related to this symbol, this is the set symbol, and for it always false for the logic value. And here is just the all set the universal set, which is always true. So here is the thing P or imperative. And imperative just means it's false. So P or F just also logically equivalent P, and P and true is logically equivalent to P. So here just similar mechanism. The same is a set identity and the logical equivalent rules.
Elements contained in both A and the universe, which would be systems in A. Combination law, I have A union the universe, which would of course be the universe, because remember, what I'm looking at with a union is anything that's in either one of those sets, and the universe would be everything that I'm dealing with, or everything that I'm concerned with. Or I could say A intersect the empty set would be the empty set, because remember, in the intersection, it must belong to both sets, and the only thing that belongs to both sets in A and the empty set is the empty set. So there's nothing that is contained in both. Idempotent laws, A union A, will that make sense? A union A would just be A. So I'm taking the same set, combined with itself, what's in both sets, or what's in either set, A. Same thing, what's in both sets of A intersect A would still be A. So it's the same idea. And the complementation law, if I'm looking for the complement of not A, we would of course end up back at A, because if I took A and I took the complement, and then I took the complement of that, I would end up back where I started. So instead of add 5 to the complement, if I take 5, I end up back where you started. And a few more laws that should be super familiar to you, because you probably started learning about these in middle school. Commutative, associative, and distributive. Obviously, these are less familiar with, but we are now talking about them in terms of sets. So the commutative law essentially says I can take the union of two sets in either order, and it's going to be the same result. So if I take A union B, that's going to equal B union A. Similarly, for A intersect B, it's going to be the same set as B intersect A. It essentially tells you you can take the union or intersection in either order, and you're going to get the same result. The associative law always has to do with grouping, so this obviously has to deal with order. Associative always deals with grouping, and with the associative law, the values will remain in the same order. Say A union B union C, where union B and C is happening first, is going to give you the same result as if I took A union B and then took the union of that result with set C. Keep in mind that if I'm dealing with a union, this is going to be a value, the result is going to be a value that's in any of those three sets. So if it's an A or B or C, it's going to be in the union of A, B, and C in whichever order you combine them in. Same thing for intersection. A intersect B intersect C is going to give me the same result as A intersect B and then intersect C. Same exact thing. I'm going to erase that line just to make it not look like a complement. And again, For something to be in the intersection of three sets, it has to be in each of those three sets. Then we have the distributive laws, and these again should look familiar. If I'm distributing the intersection over a union of sets, that's the same as me finding the intersect of each set and then taking the union of the result. Or if I'm taking the union of the intersection of two sets, I can distribute the union over those two sets, A union B, A union C, and then take the intersection of those two sets.
So this the set, the identity, it also can be referred to the logic rules. It's just the set laws and also just correspondent to the logic rule. It's just, for example, we just choose this. Here we know that this symbol is just referred to logical or in the section that intersection just the logical and so here we just means if the P as the O and then we have the Q or R. So for the associative, that means we can just to this for the group, we just but they have the same. It should be have the same. Then we can then to care about their group. That means the first to compute the QR is logically equivalent to first to compute the PQ. Then we compute with the R. They are same. And distribute that means they are different. Here is the intersection and unit, and just for just the logic, that means if they are different O, Q, and R. If you and then they are just different. That means we are just you distribute for P or Q and E or R. So it is just similar like this. Okay, and then the others also the same. Yeah.
Take a look now at just a few more set identities. And of course, we have to talk about De Morgan because De Morgan just keeps popping up. And so this same concept should look familiar to you. Remember, De Morgan has everything to do with negations and how that changes a relationship. So A union B, if I now have the complement of A union B, that's simply telling me I can take the complement of A, intersect the complement of B. So as you can see, I have a very simple example up here. We're going to call this set A and set B, just so you can see the relationship. So looking at this, set A obviously is including elements 1 and 2. Set B includes the elements 2 and 3. Set U, the universe, includes only 1, 2, 3, 4. So those are the only elements that I'm dealing with. So now if I take a look at De Morgan's first law here, it says A union B and then the intersection. I'm sorry, the complement of that. So A union B would be 1, 2, 3. Anything inside either square. But I want the complement of that. So the complement of that would be anything in the universe that's not 1, 2, or 3. So that means this is 4. Now let's take a look at the complement of A. So if A is 1, 2, the complement of A is anything besides 1 and 2, which is 3 and 4. And then I want the intersection of the complement of B. So the B is 2, 3. Right, 1 and 2 there. B is 2, 3, so the complement of B is 1, 4. And now I want the intersection of those two sets. So what do those two have in common? Just 4. So again, we can show that those are the same. It's not a proof, it's just a way to sort of visualize what's happening. In the same way that Morgan had two laws when we're dealing with propositional logic, he's also got two laws when we're dealing with set identities. So now I've got A intersect B, and I bet you can guess what's going to happen. I'm still going to have the complements of A and B, but now I'm going to take the union. So now if I'm looking at the union, let's look at the same example. I'm going to change this to intersection. So I've got A intersect B, and then I'm going to take the complement. So A intersect B is just 2. It's the only thing that A and B have in common. So the complement of that is going to be 1, 3, and 4. Anything besides 2. Now I want A union B to hopefully match up with that. So A union B would mean I'm adding the elements of this set, and that would give me A union B, where these are the complements. I'm going to have the element of 1. I'm going to have the element of 3, and 4 happens twice, but that doesn't matter. I'm going to have the element of 4, and if you'll notice, those two things are the same. So those are De Morgan's laws. Let's talk now.
Okay, for this Morgan laws, we also can use the simple ways to remember it. That means if you want to push this complement for the set operator, we can just think as a logical note. It is if we just push this and that means this all together will end for each will change. Yeah, just meet the set A, we change it to as complement. It's just to for the state operator union, it just change to the intersection, and for the B, it just change it to the it's a set complement. And here is the similar.
Now about absorption laws. So the absorption law says that if I take A union A intersect B, I'm going to get A. Or if I take A intersect A union B, I'm going to get A. So let's make these make sense. And again, you can use the specific elements from the practice set if you'd like, but keep in mind A intersect B is going to be anything that's in both A and B. And then if I'm taking A union, A intersected with something else, it really doesn't matter because anything in here is in A. And so if I take something union the set A, I'm going to end up with the set A. And here, A union B is everything that's in both A and B. If I take the intersect of that with set A, then I'm only going to be left with set A. And again, you can certainly look at our example and say, well, A is 1, 2, and I'm taking the union with A intersect B, which is 2, which of course is going to give me 1, 2, which was just set A. So I'll leave you to the other one to do on your own. Lastly, let's take a look at the complement laws. We have A union not A.
So this absorption is similar as the logical absorption rules. That means that from the left side we have the B's to computation, but finally we don't care about the B's the value. That means we don't care about B value. The finally is only depend on the A's value, and this is the same. So we can say A absorb the B's value. So it is can be seen as the absorption.
And again, this is a union. If I take A and everything that's not in A, I'm going to be left with anything in the universe. In this case, that would be 1, 2, 3, 4. If I take A intersect not A, so what's in A and not A? Not a darn thing. So that's the empty set.
So here just give you about the just the set, yeah, the set identity, and here just we also can be using the logical expression or logical the rules to understand the set is identity. And here we can be saying if just the P, this is just the similar as the O. Here we know that this is just the symbol here. Sometimes we can just the PO not P. P or not P, that means logical equivalence 2. Because we know that this U, this universal set is true. And here, just the P and not P, it is always false. So it is a complement loss. It is just referred to the seminar about the logical rules. Okay, and is to prove. And prove means that if you just use prove, you can just change to the logical expression. And based on the logical equation, we can using the logical inference for this. Okay. Okay. Now maybe we'll just have the minutes or 7 minutes discussing time. And for this Wednesday morning, we are just do our first experiment. And our experiment just do using your concrete or your favorite programming code to implement, to practice, your practice to implement the truth table, the truth table. We are just said in detail in this Wednesday morning, okay? And we have the 2 times or 2 sessions to do this experiment. After experiment, you will asked to submit your experiment report in the similar as the homework in the digital group. Okay. And we will give you a long time for your experiment report, maybe the 3 weeks for deadline for your submit after the submit. Okay. Your experiment report. Okay. Any more questions? So if you have been this is just the team talk or just have some it is a sign just the problem you can ask the teacher assistant. Any question you can ask him or you just tell him you have some input or check in, but maybe have something reason. Maybe he can just help you to by hand. Any question? Discussing time.
No.
Okay. Hello. Okay. No question. Bye bye. No questions, that's all today. Bye bye.
This lab is not good. We have to change. You have to take care and getting well and everything. Imagine every day. Doing test everything. Yes, I'm going to do. Yes. Okay. Okay, see you soon. Go away. I cut you. Fuck you.